What if climate engineering could cool the whole planet? Not merely in a computer model, and not only for a season after a great volcanic eruption, but deliberately, predictably, and with enough precision that humanity could lower the average temperature of the Earth by a fraction of a degree, hold it there, and then adjust it again. Imagine that, sometime in the second half of this century, after decades of research, argument, failed experiments, international negotiations, and increasingly dangerous heat, the technology finally became real. There would be no enormous switch mounted on a wall, no single lever labeled cooler, no machine large enough to be photographed from space. The system would be scattered across the world, aircraft designed to work in the thin air of the stratosphere, ships measuring clouds over remote oceans, satellites watching the brightness of the planet, forests and mineral fields pulling carbon from the atmosphere, laboratories testing the chemistry of every particle, and thousands of weather stations listening for changes too small for any one person to feel. And somewhere, in a quiet room filled with ordinary desks and softly glowing screens, a group of people would face the strangest decision any human beings had ever been asked to make. How cool should the world become? Tonight, let us follow that question slowly. Let your body settle into whatever is supporting you. Let your shoulders loosen. Let the day outside this room become a little less urgent. We are going to travel through a possible future, but there is nothing here you need to solve before you sleep. We will begin on a morning when the Earth has already warmed enough for the old climate to feel like a memory. For several years, heat records have been broken so often that people have stopped treating each one as surprising. Cities have painted roofs white, planted shade corridors, redesigned working hours, built cooling shelters, and moved power cables underground. Farmers use crop varieties their grandparents would not recognize. Some coastal neighborhoods have been raised behind barriers. Others have been abandoned carefully, house by house, as the sea kept arriving farther inland. Emissions have fallen sharply by then. Most electricity comes from sources that do not release carbon dioxide. Vehicles, heating systems, factories, and ships have changed. Vast industries remove carbon from the air and store it underground or in stable minerals. Yet the planet is still warm because carbon dioxide already released remains in the atmosphere for a very long time, and because oceans and ice sheets respond slowly to changes in the sky above them. The world has applied the brakes, but the enormous vehicle of the climate system has not stopped moving. Then comes a summer remembered simply as the long heat. It does not strike every place in the same way. No climate event ever does. In some regions, nights remain dangerously hot for weeks. In others, rivers fall too low for transport or cooling power stations. Mountain snow disappears early. Crops survive in one country and fail in the next. Hospitals fill. Electricity networks bend under the demand for cooling. Wildfires burn through forests that had endured fire before, but not this kind of dryness, not for this long. The disaster does not create climate engineering. The idea is already centuries old in fragments and decades old as a serious scientific debate. Researchers have studied how bright particles high in the atmosphere might reflect a small portion of sunlight back into space. They have examined whether sea salt could make certain low marine clouds more reflective. They have explored ways of removing carbon dioxide directly from the air, accelerating mineral reactions that naturally lock carbon away, restoring forests and wetlands, and changing agricultural practices so that more carbon remains in soil. These approaches have often been placed under the same broad label, climate engineering or geoengineering, though they do very different things. Carbon dioxide removal addresses part of the cause. It takes carbon out of the atmosphere and, if storage is durable, slowly reduces the pressure warming the planet. But removing enough carbon is difficult, expensive, energy-intensive, land-intensive, or all of these at once. Even a large global effort changes the climate slowly. Sunlight reflection works differently. It does not remove greenhouse gases. Instead, it changes the balance of energy entering and leaving the planet. A little more sunlight is reflected away, and the surface cools. The basic physical idea is not mysterious. Large volcanic eruptions have demonstrated it naturally. When enough sulfur reaches the stratosphere, it forms tiny droplets that scatter sunlight, and global temperatures can fall for a time. But a volcano is not a climate policy. It releases material without asking where rain should fall, how the ozone layer might respond, or what happens when the particles disappear. It cannot be paused, adjusted, inspected, or held accountable. The technology in our imagined future has been developed precisely because those differences matter. For 30 years, researchers have built ever more detailed climate models. Small outdoor experiments have tested instruments without attempting to cool the planet. Aircraft have sampled the stratosphere after volcanic eruptions. Satellites have measured clouds, aerosols, radiation, ocean heat, ice, vegetation, and atmospheric chemistry. International research teams have compared results. Independent groups have tried to find mistakes. Communities likely to experience the greatest climate risks have demanded a voice in deciding what questions were studied. At first, the debate was mostly about whether research itself was dangerous. Some feared that studying sunlight reflection would tempt governments to use it. Others feared that refusing to study it would leave the world ignorant during a future emergency, when frightened leaders might act anyway. Both fears proved reasonable. So the research developed under rules designed to make secrecy difficult. Proposed experiments were registered publicly. Data became available across borders. Funding sources were disclosed. No single company could own the central measurements. No nation could conduct a meaningful atmospheric test without international observation. The aim was not to make political conflict disappear. Nothing could do that. The aim was to prevent uncertainty from becoming someone's private weapon. By the time of the long heat, scientists understand far more than they once did. They know that a carefully controlled stratospheric aerosol program could lower global average temperature relatively quickly. They know it could reduce some extremes of heat. They also know that cooling the planet would not simply restore the previous climate in every region. A world with high carbon dioxide and reduced sunlight would not be identical to a world with low carbon dioxide and ordinary sunlight. The atmosphere would carry a different chemical history. Plants would receive slightly less direct sunlight and perhaps more diffuse light. Rainfall patterns might shift. The poles and tropics might not cool in exactly the desired proportions. Ocean acidification would continue unless carbon dioxide itself declined. Some ecological changes already underway would not reverse simply because a thermometer moved downward. And there would be another danger, quieter but more profound. Once sunlight reflection began, stopping suddenly while greenhouse gas concentrations remained high could allow temperatures to rise rapidly. The cooling particles would fall out of the atmosphere within a few years, while much of the carbon dioxide would still be there. The world would therefore be committing not only to an action, but to continuity. A generation could begin the program. Another generation might inherit the obligation to maintain it. This is why, on the morning our story begins, the room where the decision will be made does not look triumphant. The delegates are not gathered beneath banners announcing that humanity has conquered climate change. They sit beneath a plain map of the Earth. Across it move layers of information: sea surface temperatures, soil moisture, crop conditions, river flow, atmospheric circulation, hospital admissions, energy demand, coral bleaching, wildfire smoke, and the position of every aircraft and sensor that would become part of the cooling system. Outside, the city is waking beneath another hot dawn. Inside, a woman named Amara checks the translation channel in her earpiece and looks down at the document on her desk. She is not a climate scientist. She is a water negotiator from a region where rainfall has become less dependable. Her task is to speak for countries that did little to create the warming, but would live with whatever consequences the cooling produced. Across from her sits Tomas, an atmospheric chemist who has spent most of his career studying particles so small that millions could rest on the head of a pin. Beside him is Malin, an agricultural ecologist carrying maps of rice, wheat, maize, and millet regions. There are public health officials, representatives of island states, engineers, legal scholars, indigenous knowledge holders, shipping experts, ethicists, economists, and young observers who will still be alive long after most of the senior delegates are gone. They have all read the same recommendation. Begin with a cooling target of 1/10 of a degree Celsius. Not enough to undo decades of warming. Not enough to transform winter into something from the past. Just 1/10 of a degree, introduced gradually over 18 months, while emissions reductions and carbon removal continue. It sounds almost absurdly small. Most people cannot feel 1/10 of a degree in the air around them. A person walking outdoors could not tell whether the planet's global average had shifted by that amount. But the global average is not the temperature of one room or one afternoon. It is a measure of energy distributed through oceans, air, ice, and land. 1/10 of a degree across the whole planet represents an immense change in accumulated heat. The target has been chosen because it is large enough to measure clearly and small enough to stop increasing if unexpected effects appear. Amara reads the final line again. Deployment may proceed only if the Monitoring Council confirms that no region is being treated as expendable. That sentence took 11 years to negotiate. It is not a scientific statement. It is a promise. And promises, as Amara knows, are easier to write than to keep. The vote does not happen immediately. For 6 hours, the delegates ask questions whose answers have already been discussed for years. What if the particles damage ozone more than expected? What if one monsoon weakens while another strengthens? What if cooling reduces rainfall over a dry region? What if a government claims that an ordinary drought was caused by the program and demands compensation? What if the system works so well that countries delay the harder work of eliminating emissions? What if it works badly? What if it works perfectly? That last question receives the longest silence. A failed technology would be abandoned. A successful one could become permanent. It could change the meaning of climate politics from preventing damage to managing the sky. Every heat wave, harvest, flood, and storm might then be interpreted through a new suspicion. Was this still nature? Was it climate change? Or was it the thermostat? Tomas explains again how the first phase would work. A small fleet of specialized aircraft would climb into the lower stratosphere, far above ordinary weather. They would release a carefully selected precursor material in amounts tiny compared with the atmosphere itself, but large enough to form reflective aerosol particles. The release would be spread across seasons and latitudes rather than concentrated in one place. Satellites and high-altitude balloons would follow the plume. If particle size drifted away from the intended range, if ozone chemistry changed unexpectedly, or if regional climate indicators crossed agreed limits, additional releases would pause. The particles would not form a visible roof. People looking upward would see the same sky, though sunsets might become slightly more vivid in some places. The effect would emerge in instruments first. A small change in the amount of sunlight reaching the surface, a small change in the energy leaving the top of the atmosphere, then a gradual response in temperatures. Malin speaks after him. She reminds the room that the average temperature is not the only number that matters. Crops respond to sequences. A warm night after a hot day can be more damaging than the same average temperature spread differently. Rain arriving 2 weeks late can matter more than total annual rainfall. A slight reduction in heat could save one harvest, while a shift in cloud or precipitation could threaten another. Therefore, the The program cannot be judged by a single global line moving downward. The monitoring system will watch hundreds of indicators, some physical and some human. Reservoir levels, food prices, mosquito ranges, ocean heat, glacier mass, labor lost to dangerous heat, insurance withdrawals, migration pressure, ecosystem stress, the number of people able to sleep safely at night without mechanical cooling. The last measure was added after a public health researcher described heat not as a graph, but as exhaustion. Near sunset, the delegates vote. There is no cheer when the result appears. The authorization passes by a margin large enough to begin and narrow enough to reveal how uncertain the world remains. Amara presses her thumb against the identification panel, confirming her vote in favor. Then she closes her eyes for one breath. Outside the building, crowds react in opposite ways. Some embrace. Some hold signs accusing the council of stealing the sun. Some demand faster action. Others demand a permanent ban. A group of children has painted a blue circle on the pavement and written beneath it, "Please be careful with our sky." The first flight takes place 3 weeks later. The aircraft is white, long-winged, and almost disappointingly ordinary. It carries no symbol of conquest. Its crew consists of 2 pilots, an atmospheric engineer, and a systems observer. Although later aircraft will fly autonomously, the first mission includes people because the world wants witnesses. At dawn, the aircraft rises from a remote runway and climbs through the lower atmosphere. Clouds flatten beneath it. The blue above grows darker. The horizon curves gently, not enough to feel like space, but enough to remind the crew that the layer in which human life occurs is extraordinarily thin. The release begins over an empty stretch of ocean. There is no explosion, no beam of light. A fine stream enters air too dry and still to resemble the weather below. Instruments count particles, measure temperature, pressure, humidity, sunlight, and chemical reactions. Ground stations receive the data almost instantly. For 47 minutes, humanity deliberately alters the radiative balance of its planet. Then the valves close. The aircraft turns home. Nothing happens that day. Nothing happens the next day either. This surprises the public, though scientists have explained it repeatedly. The climate is not a room with an air conditioner. Oceans store enormous quantities of heat. Winds move energy across continents. Ice, soil, vegetation, and clouds respond on different timescales. Even an intervention designed to cool quickly by climate standards unfolds slowly by the standards of news. For the first month, the most visible result is argument. Markets rise and fall with rumors about new data. Religious leaders debate whether adjusting sunlight violates a boundary humans should respect. Artists project artificial sunsets onto buildings. Conspiracy theories spread faster than aerosol particles. A false report claims that birds have stopped migrating. Another says the stars are disappearing. Neither is true, but corrections travel less dramatically. The actual measurements are quieter. At the top of the atmosphere, reflected sunlight increases by a barely detectable amount. Surface solar energy declines slightly in targeted bands. Stratospheric particle distribution remains close to model predictions. Ozone chemistry changes, but within the conservative limits set before deployment. Rainfall patterns remain dominated by natural variability, too noisy for confident attribution. After 3 months, the Council authorizes the next increment. The fleet grows from 1 aircraft to 12. By the 6th month, every release is watched by several independent networks. One belongs to the international program. Another is operated by universities. A third is maintained by a coalition of countries that originally opposed deployment and demanded the ability to verify every claim. Amateur observers contribute balloon data. Commercial satellites add measurements. Ships sample the lower atmosphere beneath the flight paths. Trust does not arise because everyone agrees. It arises because disagreement can inspect the evidence. Then, during the 8th month, the first measurable cooling signal appears. It is not a dramatic fall. Global average temperature remains high. A natural ocean cycle is shifting at the same time, making interpretation difficult. But after statisticians account for known variability, the probability that the intervention is having no effect becomes very small. The planet is cooling by hundredths of a degree. The announcement is made at a press conference attended by more journalists than any scientific briefing in history. Tomas stands behind a plain lectern and says the sentence he has rehearsed all night. The system is behaving within the expected range. This is evidence of an effect, not evidence of complete safety. Most headlines use only the first half. Across the world, people step outside and look upward. They do not feel the change. A baker opening a shop before sunrise still wipes sweat from her forehead. A railway worker still checks a heat warning before beginning his shift. A child in an apartment without reliable cooling still sleeps beside a fan. The Great Cooling, as some broadcasters have already named it, is too small to touch one particular morning. But climate is built from particular mornings repeated across decades. By the end of the first year, the target is reached. The global average is approximately 1/10 of a degree cooler than it would have been without the intervention. The language matters. The world has not returned to an earlier temperature. Greenhouse gases continue to trap heat. The program has offset a small portion of that warming. The first annual report fills thousands of pages. Heat extremes have declined slightly in many regions. The number of dangerous labor hours has fallen. Some snowpacks lasted longer. Energy demand for cooling was lower than projected. Yet not every indicator improved. A seasonal rain belt shifted modestly. One semi-arid region experienced a dry year that models cannot clearly attribute to the intervention, natural variability, or both. Crop yields improved globally but declined locally. Ozone loss remained limited, though greater than the median model estimate. The world had asked whether climate engineering could cool the whole planet. Now it had an answer. Yes, and almost immediately, that answer produced a more difficult question. Should the planet be cooled further? The second vote is harder than the first. 1/10 of a degree had been presented as a test. Further cooling would become policy. Countries suffering from extreme heat ask for another 2/10 immediately. Mountain regions watching glaciers retreat ask for more. Island states point out that every fraction of a degree matters for long-term sea level, though cooling cannot instantly reverse ice already destabilized. Agricultural exporters whose harvests improved support expansion. Nations that experienced unusual drought demand delay. The Council receives petitions from people who have never before appeared in climate negotiations. Wine growers worry that cooler summers will alter grapes already adapted to warming. Hydropower operators want forecasts for snow and river flow. Solar energy companies ask how reduced direct sunlight and increased diffuse light will affect generation. Astronomers request clearer models of changes in the night sky. Public health groups calculate how many heat deaths might be avoided by another increment. Communities dependent on monsoon rainfall ask why anyone should be allowed to experiment with a system that feeds billions of people. The debate reveals something that global averages conceal. There is no single preferred climate. The climate of the past was not generous to everyone. Some regions lived with drought, hurricanes, bitter cold, or unreliable rain long before industrial warming. Cooling the planet toward a 19th century average would not recreate justice. It would recreate an average formed from unequal local conditions. And no year in the past was a perfect template. Should the target be the climate of 1850, before most industrial emissions? The climate of 1950, familiar to living memory in some countries? The climate of the year when modern monitoring became reliable? Should the goal be a temperature at all, or a set of risk limits for heat, ice, crops, water, and ecosystems? Amara begins to understand that the phrase global thermostat is misleading. A household thermostat controls one building toward one chosen temperature. The climate system has no single room and no single occupant. It is more like an immense house with billions of rooms, open windows, leaking pipes, moving walls, and inhabitants who disagree about what comfortable means. Still, refusing to choose is also a choice. Without additional cooling, dangerous heat will continue. The council cannot hide behind complexity while people die from conditions the technology might reduce. A compromise emerges. The next phase will target another 1/10 of a degree, but releases will be adjusted by latitude and season to reduce known regional imbalances. A compensation fund will begin paying for verified harms, even when attribution remains probabilistic rather than certain. Carbon removal targets will automatically rise whenever sunlight reflection expands. No country may claim cooling credits as a substitute for reducing its own emissions. The last rule becomes known as the paired obligation. For every unit of temporary cooling added through sunlight reflection, the world must commit to a corresponding increase in permanent carbon removal and emissions reduction. The rule is imperfect. Governments find creative ways to argue about what counts as corresponding. Yet it changes the political story. Climate engineering is not described as erasing carbon pollution. It is described as borrowing time, and every borrowed year carries a repayment schedule. The fleet expands again. Within 5 years, the world is roughly half a degree cooler than it would otherwise have been. This is large enough to be felt through statistics and, occasionally, through memory. Summers remain hot, but some of the most extraordinary extremes become less frequent. Cities that had prepared for an accelerating rise in cooling demand find that demand stabilizes. Nighttime temperatures fall enough in some regions to reduce mortality. Alpine snow persists several weeks longer. Sea ice recovers modestly in certain seasons, though it does not return to the extent remembered from old satellite images. Coral reefs still face stress from warm water and acidification, but fewer mass bleaching events occur during favorable years. The benefits are real. So are the differences. In the Sahel, rainfall changes unevenly. Some districts receive more dependable wet seasons, others do not. In South Asia, monsoon timing becomes the subject of daily global attention. Farmers who once watched clouds now also watch council announcements, aerosol maps, and model ensembles. In the Amazon, temperature stress eases, but forest health still depends on deforestation, fire, and rainfall. In the Arctic, cooling slows thaw in some soils, yet methane and carbon already released do not return automatically underground. The planet has not been healed by one tool. It has been moved into a different state. A new profession appears, climate attribution mediator. These specialists work between science, law, and diplomacy. When a drought occurs, they examine whether climate engineering changed its probability. When floods destroy a valley, they ask whether cooler temperatures altered atmospheric moisture, storm tracks, or snowmelt. They rarely produce simple answers. Natural variability remains powerful. Weather systems still surprise. A damaging event may have been made 10% more likely, or 20% less likely, or changed in ways models cannot resolve. Courts are accustomed to asking who caused an event. Climate attribution often answers with probabilities. The compensation fund therefore develops an unusual principle. A community does not need to prove that the intervention alone caused harm. It must show that the global program plausibly increased the risk and that the loss falls beyond an agreed threshold. Money is then paid from contributions based partly on historical emissions, partly on present wealth, and partly on the degree to which each country benefits from cooling. No one finds the formula fair. That may be why it survives. The first major compensation case comes from a chain of inland farming districts where rainfall declined over 3 consecutive seasons. Models disagree about the role of sunlight reflection. The global average suggests agricultural benefit, but local reservoirs are empty. Families are selling livestock. Young people are leaving. At the hearing, a farmer named Idris speaks through a remote connection. He does not discuss radiative forcing. He holds up a jar of dust taken from a field where his family once grew sorghum. "You say the world is safer," he tells the council. Perhaps it is, but safety that exists only in the average cannot feed my children. The sentence is repeated everywhere. The council approves compensation, funds new water infrastructure, and modifies the seasonal pattern of aerosol release. Scientists caution that no adjustment can guarantee rain in one district without influencing circulation elsewhere. Yet the program changes. This becomes one of its defining features. The thermostat is not set once. It is negotiated continuously. Every year, the council publishes several possible pathways. Hold temperature steady. Cool another tenth. Reduce intervention while carbon removal catches up. Shift particles toward one hemisphere or the other. Change particle composition to lessen ozone effects. Use marine cloud brightening regionally instead of adding more stratospheric aerosol. Each option includes maps of likely benefits, risks, and uncertainty. Public assemblies review the choices. Citizens are selected by lottery in hundreds of countries and given months of education before deliberating. Their recommendations are not legally binding, but ignoring them has political cost. People who once felt climate policy was distant now argue about aerosol residence time at kitchen tables. The process is slow, frustrating, and vulnerable to manipulation. It is also the first time humanity has attempted to govern a planetary system with something approaching planetary consent. Not everyone participates. One powerful nation leaves the council after accusing it of limiting national sovereignty. Its leaders announce that they will operate their own regional cooling program to protect crops and reduce hurricane risk. Scientists warn that regional atmospheric interventions do not remain neatly inside borders. Winds do not carry passports. For several months, the world faces the possibility of competing skies. The breakaway government prepares aircraft. Neighboring countries threaten sanctions. Satellite images of new facilities spread across news networks. Military planners quietly ask whether an aerosol aircraft should be treated as civilian climate infrastructure or a strategic weapon. Amara travels to the capital with a small delegation. She meets officials in a windowless room where a model of the planet rotates above the table. They tell her the international process is too slow. Their citizens are dying in heat waves. Their harvest losses are unacceptable. They possess the technology and have a duty to act. Amara does not deny the emergency. Instead, she asks them to imagine that another country, one they distrust, made the same claim and altered the atmosphere without consultation. The room grows quiet. Sovereignty, she says, cannot mean control over air that will circle the globe. After weeks of negotiation, the nation returns under a revised agreement that gives regions faster emergency review while preserving common monitoring. The crisis passes, but the lesson remains. Climate engineering has lowered the physical cost of changing global temperature. It has not lowered the political cost of deciding who may do it. In fact, success has made that question more urgent. As the system proves dependable, private companies enter the field. Some build sensors. Some design aircraft. Some develop particles intended to reflect more sunlight with less chemical effect. Others offer climate services to cities, farms, and insurers. Most perform useful work. A few promise impossible precision. One company advertises regional weather stabilization. Its images show green fields, calm skies, and rain falling exactly where requested. Scientists call the campaign misleading. The atmosphere cannot be programmed like irrigation. The company replies that old institutions are protecting their monopoly. Investors send billions. The scandal that follows is not a technological disaster. It is a data disaster. Investigators discover that the company suppressed model runs, showing increased drought risk outside its target region. No particles were released, but public trust collapses. For the first time, the council pauses all expansion while every contractor is audited. The pause lasts 9 months. Global temperature rises only slightly because existing aerosols remain, but the event exposes the dependence beneath the calm. Airlines, agriculture ministries, and health agencies have already built plans around continued cooling. Insurance prices react. Food markets become nervous. Governments demand reassurance that the program will not be interrupted by politics or corruption. The world had thought the dangerous moment would be deployment. Now it realizes that maintenance may be even more delicate. The pause also produces the outcome climate activists had feared from the beginning. Several governments announced that because the planet is no longer warming as rapidly, expensive emissions targets can be relaxed. Fossil fuel companies describe sunlight reflection as proof that continued extraction is compatible with a stable climate. Airlines argue that synthetic fuels can wait. Industries facing difficult transitions ask for another decade. The argument is tempting because the cooling is visible in global temperature records. The line that once climbed year after year has flattened. Some years are warmer, some cooler, but the relentless rise appears to have stopped. To many people, the emergency feels less immediate. This is the moral hazard becoming real. It does not require anyone to believe climate change was a hoax. It requires only the ordinary human tendency to postpone painful work once immediate danger seems reduced. The paired obligation was designed to prevent this, but laws are not self-enforcing. Carbon removal projects are behind schedule. Some storage sites perform well. Others are delayed by cost, public opposition, energy shortages, or unrealistic promises. Forest programs struggle where land rights were ignored. Direct air capture expands. Yet pulling carbon dioxide from thin air requires vast infrastructure and clean energy. Enhanced weathering works in some soils and watersheds, but raises questions about mining, transport, and ecological effects. Ocean-based methods remain especially controversial because marine systems are complex and difficult to monitor. Cooling the planet turns out to be faster than cleaning the atmosphere. That imbalance reshapes politics. A new coalition forms among countries most vulnerable to long-term sea level rise and ocean acidification. They are grateful for reduced heat, but they reject the idea that temperature alone measures success. Carbon dioxide dissolving into seawater continues altering ocean chemistry. Even if surface temperatures are held steady, marine organisms that build shells or skeletons from calcium carbonate remain under pressure. Coastal communities still face seas that respond slowly to earlier warming. Ice sheets do not instantly regrow. The climate debt has not disappeared. Part of it has changed form. At the next council meeting, an island representative places 2 transparent vessels on the table. One contains ordinary seawater. The other contains seawater adjusted to the acidity expected if carbon dioxide remains high for decades. Between them lies a small shell, pale and fragile. "You have cooled the air above our ocean," she says. "Now remove what is changing the water beneath it." The image becomes as influential as Idris's jar of dust. The council responds by rewriting the program's central metric. Success will no longer be reported primarily as degrees of cooling. It will be described through a planetary recovery dashboard: atmospheric carbon concentration, global temperature, ocean heat, ocean acidity, ice mass, ecosystem integrity, human heat exposure, and regional water security. The new dashboard is less satisfying than a single line. That is its purpose. A planet cannot be represented honestly by one number, even when that number is important. Carbon removal becomes the largest infrastructure project in human history. The work does not look the same everywhere. In basalt regions, carbon dioxide is dissolved in water and injected underground, where it reacts with rock and becomes mineral. Near industrial clusters, pipelines carry concentrated carbon to carefully characterized geological formations. In dry regions with abundant clean energy, direct air capture machines draw air through chemical filters. On degraded land, restoration projects rebuild soil, vegetation, and water retention, though governments finally stop pretending that every tree planted is permanent carbon storage. In coastal wetlands, mangroves and marshes are restored for carbon, storm protection, fisheries, and habitat. The best projects provide several benefits at once. The worst repeat old patterns. Land taken from communities promise jobs that never arrive. Monoculture plantations counted as forests, storage contracts signed without long-term liability, mining expanded in places with little political power. Climate engineering has not removed the need for justice. It has multiplied the places where justice must be practiced. Young people begin to describe the era as the Great Maintenance. Their grandparents built economies around extracting and burning ancient carbon. Their parents built systems to stop the temperature from rising. Their generation must maintain cooling while removing the accumulated gas, restoring damaged systems, and preventing political collapse around a technology they did not choose to begin. Some resent the inheritance. At universities, students march beneath signs that read, "We were born under someone else's sky." They do not necessarily demand that the program end. Most understand the risk of sudden termination. They demand representation proportional to the future they will carry. The council reforms again, reserving seats for delegates under 30 and requiring every major decision to include projections extending beyond the lifetimes of current leaders. One of those new delegates is a young systems engineer named Lien. She was 6 years old during the first deployment. She remembers adults standing outside and looking upward, though she could not understand why. To her, the managed climate is not an intervention. It is the background condition of life. Lien specializes in failure. Her team asks what happens if aircraft fleets are grounded by war, if supply chains for critical materials collapse, if satellite networks fail, if a cyber attack corrupts measurements, if a pandemic reduces staffing, if a volcanic eruption adds unexpected aerosols, or if several problems happen at once. The original program was designed around scientific uncertainty. Lien argues that it must now be designed around civilizational uncertainty. She proposes strategic reserves of required materials on every continent, multiple aircraft designs using different supply chains, manual backup systems, independent navigation, analog instruments stored against digital failure, and training programs that can rebuild lost expertise. She wants no component so specialized that only one factory knows how to make it. Her colleagues call this the continuity architecture. It is expensive, redundant, and inelegant. The council approves it almost unanimously. For several years, the climate program enters a stable phase. Emissions continue falling after the temporary political slowdown. Carbon removal expands. Atmospheric carbon dioxide finally reaches a broad plateau. The cooling target remains fixed rather than deepening. People adapt to the idea that the intervention is a bridge, not a destination. And ordinary life changes in ways no early report predicted. Weather forecasts now include two baselines: conditions under the managed climate and an estimate of what conditions might have been without intervention. School children learn to read both. Museum exhibits display the first aerosol aircraft beside coal engines and early solar panels. Insurance contracts specify which climate baseline applies. Farmers receive seasonal guidance that includes uncertainty from natural variability, greenhouse forcing, and intervention effects. Language changes too. People stop saying natural weather when they mean weather without direct intervention, because there is no untouched atmosphere left to compare with. Industrial emissions had already altered the climate before anyone attempted cooling. Instead, scientists speak of unmanaged and managed trajectories. This distinction matters. The first form of climate engineering was not the cooling program. It was the accidental warming produced by centuries of emissions, carried out without a global vote, without monitoring designed for consent, and without compensation for those most harmed. The deliberate program feels more unsettling because intention is visible. A smokestack did not announce that it was adjusting planetary temperature, though billions of smokestacks together did exactly that. The aircraft in the stratosphere make the choice impossible to ignore. For some philosophers, this visibility is a moral improvement. Humanity can no longer pretend that climate is separate from human action. For others, it is a dangerous expansion of control, encouraging the belief that every planetary limit can be managed technologically. Religious traditions respond in different ways. Some describe the program as stewardship, a reluctant effort to reduce damage caused by human carelessness. Some call it arrogance, the transformation of the heavens into infrastructure. Many hold both ideas at once. In one city, a yearly ceremony develops on the anniversary of the first flight. At sunset, all cooling aircraft pause releases for several minutes, not long enough to affect climate, but long enough to mark dependence. Bells ring. People stand outside. Names of those lost in climate disasters are read aloud, followed by the names of technicians, farmers, firefighters, researchers, and community organizers involved in recovery. The ceremony does not celebrate mastery. It remembers responsibility. Then, in the 23rd year of the program, a great volcano erupts. The eruption occurs in a region with sparse monitoring and little warning. A column of ash and sulfur rises high into the stratosphere. Within hours, satellites confirm that the natural injection is large enough to produce additional global cooling. For the first time, the human-made system must respond to a planetary intervention performed by the Earth itself. All scheduled releases stop. Aircraft shift from deployment to measurement. Balloons rise from dozens of sites. Climate models run continuously. The volcano's plume spreads unevenly, shaped by winds, particle chemistry, and season. Sunsets deepen to red and violet. The public can finally see something resembling the process that has been managed invisibly for decades. Temperatures begin to fall more than intended. The change is still modest by the standards of daily weather, but agriculture notices. In high latitudes, growing seasons shorten. Solar generation declines slightly in some regions. Stratospheric chemistry becomes more concerning. The Council faces an unfamiliar task. Not how to cool the world, but how to avoid overcooling when the cooling source cannot be switched off. The continuity architecture helps. Food reserves are released. Planting guidance changes. Energy systems compensate. No additional aerosols are added for nearly 2 years. Carbon removal continues. When the volcanic particles finally begin to settle, human deployment resumes gradually. The event teaches 2 lessons. First, the managed climate remains part of a living planet that can surprise its managers. Second, the ability to pause is as important as the ability to act. Afterward, every major proposal must include not only a deployment plan, but a restraint plan. How to do less, how to wait, how to recognize when natural systems are already producing the desired effect. For a civilization accustomed to measuring progress through expansion, this may be the most difficult form of engineering of all, the engineering of enough. As the volcanic haze fades, researchers return to a question that had seemed almost secondary during the emergency years. What does a slightly dimmer world feel like to living things? The change in sunlight is small. In most places, no one can see it directly. Yet ecosystems are built from tiny differences repeated across seasons. Plants respond not only to temperature and carbon dioxide, but to the amount and quality of light. Some benefit from a larger share of diffuse sunlight, which penetrates deeper into dense canopies. Others depend on intense direct light. Insects time emergence by temperature, day length, and food availability. Birds migrate using cues that may not shift together. Coral reefs experience temperature relief, but remain exposed to acidifying water. Snow reflects sunlight naturally, so recovering snow cover adds its own cooling feedback. There is no universal ecological response. In the first decades, many species benefit because the pace of warming slows. Mountain animals retain cold habitat longer. Forests experience fewer extreme heat events. Wetlands lose water more slowly. Some reefs gain precious recovery years between marine heat waves. The intervention does not restore extinct species or rebuild fragmented habitat, but it reduces one pressure among many. Then subtler effects emerge. A flowering plant in one region begins opening several days earlier because spring temperature has changed, while its pollinator follows day length and arrives on the old schedule. A migratory bird reaches a stopover site after the insects it feeds on have already peaked. In another place, cooling repairs a mismatch created by warming. The same intervention can separate one relationship and restore another. Ecologists insist that the Climate Council stop speaking about biodiversity as though it were a single quantity that rises or falls. The Council creates a living observatory network stretching from tropical forests to polar seas. Local communities become central partners because no satellite can notice every change in nesting, flowering, migration, soil moisture, or animal behavior. Indigenous observers contribute records extending beyond modern instruments. Fishers report shifts in currents and spawning. Farmers document pests. Children in schools count butterflies and track first frost. The data reveal a humbling truth. The climate system can be measured globally. Life must also be understood locally. This changes how the program is adjusted. Earlier decisions were dominated by global temperature and precipitation models. Later decisions include ecological thresholds, migration corridors at risk, forests nearing fire transition, fisheries under stress, ice-dependent breeding grounds, and regions where cooling might create new mismatches. The atmosphere cannot be tuned separately for every species, but the intervention can be paired with habitat restoration, wildlife corridors, water management, and reduced pollution. Climate engineering becomes less like a standalone technology and more like one layer in a much larger repair effort. The same pattern appears in agriculture. At first, global crop production rises modestly because extreme heat becomes less frequent. Wheat in some temperate regions benefits. Livestock mortality falls. Irrigation demand declines in certain basins. Yet carbon dioxide remains high, affecting plant growth and nutritional quality. Rainfall remains uneven. Pests and diseases respond differently from crops. Some regions gain longer stability. Others face new uncertainty. Malin, now older and serving as senior advisor, spends much of her time correcting a simple public story. Cooling does not mean returning farms to the past. Seeds have changed. Soils have changed. Water tables have changed. Rural populations have changed. Markets have changed. A region that once grew a particular crop may no longer have the people, infrastructure, or knowledge to grow it at scale. Climate is one condition among many. She visits Idris's district years after the compensation case. The new water system is functioning. Farmers have shifted to crops better suited to variable rainfall. Some young people have returned. The aerosol schedule was adjusted, though no one can prove that the adjustment caused the improved seasons that followed. Idris is older now. He takes Malin to the field where he filled the jar with dust. Sorghum is growing again, not as it did in his childhood. The rows are different. The seed variety is different. Moisture sensors stand between plants. A community reservoir glints beyond the field. Did the sky save us? Malin asks. Idris smiles. The sky gave us time, he says. People did the rest. That sentence becomes another principle of the era. Cooling can create time. It cannot decide how time is used. Some governments use the reprieve to strengthen health systems, redesign cities, restore watersheds, and reduce inequality. Others use it to postpone reform. Wealthy districts become greener and cooler while poor districts remain exposed. Insurance returns to some coastal areas, but not others. New infrastructure protects financial centers before informal settlements. The atmosphere is managed globally, yet adaptation remains uneven street by street. A political movement emerges around what it calls temperature justice. Its leaders argue that lowering the global average is not enough if people still experience heat according to income. They demand shade, housing standards, public cooling, safe working hours, access to water, and energy systems that do not fail during heat waves. They point out that a cooled planet can still contain dangerously hot factories, prisons, refugee camps, and apartments. The movement changes climate policy again. The Council begins reporting not only average heat exposure, but unequal heat exposure. Maps show who lives near trees, who works outdoors, who can afford cooling, who loses electricity first, and whose neighborhood absorbs more heat from concrete. This makes the success story more complicated. It also makes it more honest. By the 30th year, children learn 3 separate climate histories. The first is the history of natural variation: ice ages, warm periods, volcanoes, ocean cycles, and orbital changes. The second is the history of accidental human influence: deforestation, industrial emissions, aerosols, land use, and the warming produced by greenhouse gases. The third is the history of deliberate management: carbon removal, sunlight reflection, ecosystem restoration, adaptation, and the institutions created to govern them. Teachers ask students to compare the 3. One student notices that the boundary between accidental and deliberate is not always clear. Air pollution once cooled some regions by reflecting sunlight, though no one intended it as climate policy. Removing that pollution improved health, but revealed some warming that had been hidden. Forest planting changes rainfall as well as carbon. Irrigation cools land locally. Cities change clouds. Humanity had always altered climate in fragments. The new era differs because the intention is planetary. This intention produces a culture of vigilance. Every unusual season brings questions. A hurricane intensifies rapidly, and commentators blame the council before scientists have completed analysis. A mild winter saves energy, and supporters claim success, though natural variability explains much of it. A drought occurs during an election, and candidates accuse one another of manipulating release schedules for political advantage. Most accusations are false. A few are not entirely imaginary. Internal records eventually reveal that a regional office delayed publishing a model showing increased drought risk because negotiators feared disruption before a major vote. No data were altered and no deployment decision changed, but the concealment violates the Transparency Charter. Amara, now chair of the Oversight Tribunal, presides over the investigation. She has spent most of her career defending the idea that global management can remain accountable. The scandal feels personal. At the final hearing, she says something that becomes required reading for every climate official. A system powerful enough to alter the sky must be designed for the day when good people become afraid to tell the truth. The office is restructured. Whistleblower protections expand. Independent scientific teams receive automatic access to raw data. No political body can delay publication of safety indicators beyond 72 hours. The reforms slow decision-making. Again, that is partly their purpose. Speed was essential during the long heat. Permanence requires friction. This is one of the paradoxes of governing climate engineering. The technology must respond quickly to physical danger while moving slowly enough to resist political panic. It must be stable but adjustable, global but locally informed, scientifically led but democratically controlled, protected from sabotage but open to inspection. No institution had ever carried all of these demands at once. The Council survives not because it solves the contradiction, but because the world recognizes that no simpler alternative is safer. Then a new generation of cooling technology appears. Instead of relying mainly on sulfur-based aerosols, researchers develop particles with different optical and chemical properties. In models, they reflect sunlight efficiently while reducing some risks to ozone and stratospheric heating. But they are unfamiliar materials. Their behavior in the atmosphere is less proven. Some could produce unexpected chemical reactions. Others might clump, fall faster than expected, or interact with clouds. A debate begins between improvement and familiarity. The older system has known disadvantages. The new system promises fewer, but carries unknown ones. Tomas, now near retirement, testifies before the Council. When a technology supports the climate of the entire planet, he says, novelty is not automatically progress. But neither is familiarity automatically safety. The Council approves only a tiny comparative trial under intense observation. For 2 years, the new particles are tested in amounts too small to affect global temperature. Results are promising but incomplete. The program does not rush. People complain that the Council has become timid. Perhaps it has. A civilization that once changed the atmosphere accidentally and rapidly has learned to feel nervous about deliberate change. That nervousness may be one of its greatest achievements. The greatest test of that nervousness begins with a number that should not exist. At 3:17 Coordinated Universal Time, one of the independent monitoring networks reports a sudden rise in stratospheric aerosol concentration over the northern Pacific. The increase is small, but no authorized aircraft is operating there. A second network confirms the signal. Then a third. Within minutes, the Continuity Center wakes senior staff across 4 continents. The first assumption is instrument error. The second is volcanic activity. The third is an unauthorized release. Weather satellites detect a high-altitude aircraft descending toward a private airfield on an island whose government denies all knowledge of the flight. Flight records have been falsified. The aircraft's identification system was disabled. Samples collected later confirm that it released reflective particles closely related to those used by the international program. The amount is far too small to change global climate meaningfully. The political effect is enormous. Someone has demonstrated that climate intervention can be copied. For decades, the official program had been protected by its scale, transparency, and specialized infrastructure. Yet the underlying concept was never secret. Aircraft, aerosol chemistry, and atmospheric models existed across the world. The Council could govern its own fleets. It could not erase knowledge. A group calling itself the Guardians of Winter claims responsibility. Its manifesto argues that the Council has cooled too slowly, sacrificing lives to bureaucracy. The group promises further releases unless the global target is lowered by another half degree. It includes former engineers, climate activists radicalized by disasters, and wealthy supporters who believe emergency justifies unilateral action. Governments call it atmospheric terrorism. The group calls it rescue. The Council faces a delicate response. If it treats every unauthorized gram as an act of war, it may militarize the sky permanently. If it responds weakly, copycat interventions may follow. Aircraft designed for climate work could become targets. Research laboratories could be raided. Scientists could be treated as security threats. Lien leads the technical investigation. She discovers that the aircraft was assembled from commercially available high-altitude components. The particles were produced in a laboratory that had previously worked on industrial coatings. Navigation used open-source software. None of this required the official program's most advanced capabilities. The barrier to planetary influence has fallen. Not enough for one group to control global temperature, but enough to create fear, confusion, and diplomatic conflict. The Council responds in three ways. First, it strengthens tracking of high-altitude flights and precursor materials, while preserving legitimate research. Second, it creates an amnesty channel for anyone inside unauthorized projects to report plans before release. Third, and most controversially, it publishes more technical information rather than less. Security agencies object. Why teach potential imitators? Lian argues that secrecy would create a dangerous asymmetry. Governments and wealthy actors would retain knowledge, while the public lost the ability to verify claims. Open methods allow independent detection. They make it harder for anyone to exaggerate what a small release can accomplish. They prevent mystery from becoming power. The decision echoes the early research debates. Knowledge can enable action. It can also enable accountability. The Guardians of Winter attempt a second flight 6 months later. This time, technicians inside the project use the amnesty channel. The aircraft is intercepted before takeoff. No one is killed. Several organizers are arrested. At trial, one defendant is a doctor from a city devastated during the long heat. She describes treating patients in corridors when the hospital cooling system failed. She watched elderly people die because the world moved too slowly. She believed another half degree of cooling would save millions. The court does not dismiss her grief. It also does not accept her authority to choose for everyone. She is convicted, but the judgment includes a recommendation that emergency review procedures be strengthened. The council adopts it. The crisis leaves a lasting mark. Climate aircraft are now accompanied by unarmed inspection drones. Every release is cryptographically signed and broadcast publicly. Schools teach students how to distinguish authorized monitoring data from fabricated claims. International law treats unauthorized large-scale atmospheric intervention as a crime against shared planetary systems. Yet the deeper vulnerability cannot be legislated away. Once humanity learns how to cool the planet, the possibility remains. The knowledge joins other forms of power that civilization must govern without being able to forget: nuclear physics, genetic engineering, cyber warfare, artificial intelligence. Ignorance is no longer available as protection. The only durable defense is a world in which fewer people believe unilateral action is their only remaining option. This shifts attention back to the unequal harms the program was meant to reduce. The Council increases regional representation and creates rapid response climate assemblies that can be convened after major disasters. Compensation becomes faster. Data are translated into local languages. Communities receive funding to operate their own monitoring stations rather than relying entirely on distant institutions. The atmosphere remains global. Trust must be built locally. Years pass. Atmospheric carbon dioxide begins, at last, to decline visibly. The change is slow enough that older people remember waiting for it, as one might wait for a distant tide to turn. Emissions are now near zero in most sectors. Remaining releases from agriculture, aviation, industry, and land use are balanced by durable removal. Direct air capture plants operate beside renewable and nuclear energy systems. Mineralization fields have expanded. Forest and wetland restoration continues, though carbon accounting has become stricter and less optimistic. For the first time since the industrial age began, the concentration curve bends downward for many consecutive years. This creates the possibility everyone had discussed, but few expected to witness. The cooling program might eventually be reduced. The original promise was that sunlight reflection would buy time while the underlying cause was addressed. If carbon dioxide falls far enough, maintaining the same aerosol level would overcool the planet. Releases must decline. The Council begins planning what it calls the long descent. No sudden termination. No triumphant switch off. A gradual reduction over decades, matched to falling greenhouse forcing and observed climate response. The phrase descent is chosen carefully. It refers to aerosol deployment descending, not temperature. The goal is to keep global temperature broadly stable while the source of cooling shifts from reflected sunlight to lower greenhouse gas concentrations. In theory, the transition is elegant. In practice, every step reopens old arguments. Countries that benefited most from cooling fear any reduction. Regions that experienced rainfall disruption demand faster phase-out. Industries built around the program resist contraction. Workers ask what will happen to their jobs. Aircraft manufacturers lobby for continued operation. Some scientists warn that carbon removal may be less durable than reported. Forests can burn. Political commitments can reverse. Geological storage is more secure but still requires monitoring. The world has created an industry whose ideal success would make part of itself unnecessary. This is rare enough to be politically difficult. Lien proposes a rule. Every reduction step must be reversible for 5 years. If temperatures or regional indicators move unexpectedly, deployment can return temporarily to the prior level. Strategic reserves remain available. Monitoring becomes more intense, not less. The first reduction is almost unimaginably small. Aerosol release declines by 2%. No one feels it. Global temperature remains stable. Ozone indicators improve slightly. Direct sunlight increases by a barely measurable amount. The Council waits 3 years before approving the next step. This pace frustrates nearly everyone. But stability is the objective. During the 7th reduction cycle, a cluster of storage sites reports discrepancies. Carbon dioxide, thought to be mineralizing underground, is reacting more slowly than expected. No dangerous leak occurs, but permanence estimates must be revised. The Council pauses the descent. Critics say this proves the world can never escape aerosol dependence. Researchers disagree. The problem is specific, not universal. Storage standards improve. Other mineralization sites perform well. Additional removal compensates for the shortfall. The pause lasts 4 years. Then reduction resumes. A generation grows up watching the aerosol fleet become smaller. The oldest aircraft are retired and placed in museums. Pilots retrain for atmospheric research, disaster response, and high-altitude transport. Manufacturing plants shift towards sensor systems and carbon removal equipment. The continuity architecture remains, but it becomes quieter. Children ask why the world once needed thousands of flights to hold temperature steady. Their teachers explain carbon dioxide, sunlight, and the long heat. They explain that the cooling program prevented suffering, created new risks, and demanded cooperation on a scale humanity had never attempted. They do not describe it as salvation or mistake. They describe it as an emergency bridge built while people were already crossing the ravine. Some beams were added too late. Some were placed badly. Some workers argued while others fell. But the bridge held long enough for a safer road to be built beneath it. Not everyone accepts this interpretation. A political movement called Keep the Shield argues that the program should never end. Even with lower carbon dioxide, they say, a cooler planet has advantages: fewer heat deaths, reduced cooling demand, slower sea level rise, and less stress on some ecosystems. Why surrender a tool that works? Another movement, Restore the Sun, demands complete phase-out. Its members argue that no generation has the right to dim sunlight indefinitely, even slightly. They emphasize ozone, altered rainfall, ecological uncertainty, and the danger of permanent governance over the sky. Between them stands the majority, uncertain and tired. For decades, people had feared warming. Then they feared intervention. Now they fear the end of intervention. Amara, long retired, watches the debate from her home. She is nearly 90. On her wall hangs a photograph of the first council room and the map that glowed above it. She remembers the children's message painted outside. Please be careful with our sky. A journalist asks whether she regrets voting yes. Amara looks through the window at an ordinary afternoon. The temperature outside is lower than it would have been without the program. The carbon concentration is lower than it was 20 years before. Millions of people are alive who might otherwise have died in extreme heat. Some communities were harmed by shifts the program likely contributed to. Some were compensated. Some were not compensated enough. The world remained unjust, but perhaps less damaged than it would have been. Regret is too simple, she says. So is pride. Then she adds, we were asked to choose without innocence. That is what climate change had already taken from us. The interview is replayed for years. Without innocence. It means there was no path that left the atmosphere untouched. Continuing warming was a choice. Cooling was a choice. Delay was a choice. Research was a choice. Ignorance was a choice. Every option carried risk because earlier generations had already changed the conditions under which later generations would decide. The climate engineering era did not begin when the first aircraft released particles. It began when humanity realized that even refusing to act would shape the planet. The long descent continues for another 20 years. By then, the world has changed so thoroughly that comparing it with the years before intervention becomes difficult. Coastlines have moved despite slower sea level rise. Some cities are protected by barriers and restored wetlands. Others have retreated inland, leaving old streets beneath shallow water. Northern shipping routes open less often than early projections once suggested, but more often than in the 20th century. Forest boundaries have shifted. New agricultural belts have formed. Energy systems are cleaner, more distributed, and designed for both heat and cold extremes. The managed climate did not freeze history at the moment deployment began. It merely changed the direction and speed of some changes. This distinction becomes important when people begin attributing every improvement to the cooling program. Heat deaths fell partly because temperatures stabilized, but also because homes improved, electricity became more reliable, cities added shade, and public health systems learned to respond. Crop losses declined partly because extreme heat eased, but also because seeds, irrigation, storage, trade, and soil management changed. Wildfire risk shifted with temperature, yet forest practices and land use mattered enormously. Coral survival depended on fewer marine heat waves, but also on water quality, fishing pressure, restoration, and declining carbon dioxide. The program's greatest benefit may not have been cooling alone. It forced civilization to observe the planet as a connected system. Before deployment, ministries often worked separately. Agriculture considered crops. Energy considered supply. Health considered hospitals. Water agencies considered reservoirs. Climate science connected them in models, but governments divided them in budgets. Planetary management made separation harder to maintain. A change in aerosol release could affect solar energy, rainfall, crops, health, ecosystems, and diplomacy. Decisions required shared data. Institutions that once met only during disasters began working continuously. This coordination outlasts the intervention itself. Yet there is a cost to seeing the world as a system. Systems can make people look like variables. During one council review, an optimization model recommends a release pattern that would minimize total global harm. It predicts fewer heat deaths, higher overall crop production, and reduced ice loss. But the same pattern increases drought risk across several politically weak regions. The global result is better. The distribution is worse. Some officials argue that compensation can address the imbalance. Amara's old principle appears on screens throughout the chamber. No region may be treated as expendable. Lian, now chairing the session, rejects the optimized pathway. A journalist asks whether she has sacrificed more lives globally to avoid concentrated harm locally. She answers that the model has not counted every kind of harm. It has assigned numerical values to migration, cultural loss, food insecurity, and political instability, but the values are choices disguised as mathematics. Optimization can tell us what follows from our priorities, she says. It cannot choose the priorities without us. The Council adopts a new requirement that every model display not only the best global outcome, but the people and places carrying its cost. This practice spreads beyond climate policy. Health systems, urban planning, and artificial intelligence begin using similar distribution maps. The atmosphere teaches governments to ask a question they had often avoided. Better for whom? As aerosol deployment declines, the physical differences between regions become subtler, but the political sensitivity grows. A small release adjustment can now be detected quickly in sunlight measurements, though its weather effects remain difficult to separate from natural variability. Public attention magnifies each change. Then a proposal arrives from a group of polar nations. They want to preserve a limited high-latitude cooling program after global phase-out. Their argument is practical. The Arctic and parts of the Antarctic remain warmer than historical conditions because polar regions respond strongly to greenhouse forcing and because ice loss has changed reflectivity. Targeted cooling, they say, could protect remaining ice and slow sea level rise with less influence on tropical rainfall. Other countries object. The atmosphere does not stay neatly at high latitudes. Any intervention might affect circulation farther away. Keeping regional cooling could also create a permanent class of climate-managing states with special power over the planet. For 2 years, the proposal dominates debate. Scientific studies suggest some potential, but uncertainty remains. Legal scholars cannot agree on who would own responsibility for effects beyond the target zone. Indigenous communities in the Arctic reject being treated merely as guardians of global ice. They demand authority over decisions affecting their skies, lands, animals, and seasons. The proposal is eventually narrowed to research and ecosystem support rather than deployment. The decision disappoints those who hope technology could preserve every remaining piece of ice. It reflects a deeper change in philosophy. The world no longer assumes that because something can be cooled, it should be managed indefinitely. Sometimes the task is to reduce the cause, protect what can be protected, and accept that not every loss can be reversed without creating new risks. This maturity is tested during the 48th year of the program, when a conflict between two major powers disrupts global communications. The conflict does not begin over climate engineering. It begins with territory, trade, and old grievances. But satellites are jammed. Undersea cables are damaged. Cyber attacks spread through energy and navigation networks. For several days, the climate monitoring system fragments into regional pieces. The aerosol fleet automatically enters safe mode. No new releases occur without verified data from multiple independent networks. Aircraft land or continue only measurement missions. Strategic reserves remain untouched. The physical climate is in no immediate danger. Aerosols persist for months to years, not hours. Yet no one knows whether the conflict will last weeks or decades. If global coordination collapses completely, while carbon dioxide remains above the final safe threshold, the long descent could become an uncontrolled stop. Lian activates the continuity architecture designed in her youth. Analog observatories begin transmitting through shortwave radio. Research ships carry data physically between disconnected networks. Weather balloons use prearranged frequencies. Retired engineers return to regional centers. Printed manuals are opened from sealed archives. Independent laboratories compare chemical samples without relying on the central database. For the first time in decades, the climate program operates without a single global digital picture. It becomes slower and less precise, but it does not fail. The conflict continues for 7 months. During that time, regional climate teams maintain only the minimum releases needed to avoid a sharp temperature change. No government can secretly expand the program without detection from neighboring observatories. The redundancy that once seemed wasteful becomes the difference between continuity and panic. Eventually, a ceasefire restores communications. When the global map reappears on the council wall, some values differ slightly among networks. None differs enough to threaten stability. Lien sits alone in the room after the others leave. She looks at the layers of data returning one by one: temperature, radiation, ozone, ocean heat, rainfall, aerosols. For most of her life, she had treated redundancy as engineering. Now she understands it as memory. The system survived because knowledge had not been stored in one place, one network, one institution, or one generation. Skills had been copied. Manuals had been printed. Instruments had remained independent. People who disagreed politically still knew how to measure the same sky. The lesson resembles the survival of any library, language, seed bank, or culture. What must endure cannot depend on a single keeper. After the conflict, the Council accelerates neither deployment nor phase-out. It spends 5 years strengthening continuity again. Critics call this delay excessive. But the crisis has exposed something important about termination shock. The danger is often described physically: stop the aerosols while greenhouse gases remain high, and warming could return rapidly. Yet the deeper danger is institutional. A program that requires generations of maintenance must survive wars, recessions, political revolutions, technological changes, and ordinary neglect. The safest climate intervention is not merely one with good particles and accurate models. It is one whose failure modes remain manageable when civilization behaves like civilization. Messy, divided, forgetful, occasionally wise. Carbon removal continues throughout the delay. When the phase-out resumes, the margin of safety is larger than before. Aerosol flights become rare. Most of the remaining work is performed by a few missions each season, correcting small differences between the falling greenhouse effect and the desired temperature path. The once enormous fleet is now mainly a reserve. People notice that sunsets have changed again. During the peak intervention years, some regions experienced slightly richer twilight colors as high particles scattered light. The effect was never uniform and often difficult to distinguish from dust, pollution, smoke, or volcanic aerosols. Now photographers claim that sunsets look sharper, less diffused. Scientists caution against certainty. Memory, too, has natural variability. Still, the returning sunlight becomes a cultural symbol. Songs are written about it. A popular novel follows a family across 4 generations, each seeing a different sky. Artists create installations in which rooms gradually brighten over hours. Couples choose the date of the final scheduled release for weddings years in advance, though officials repeatedly warn that the date may change. The world is preparing emotionally for the end of a system that most people once feared to begin. And beneath the celebration lies a quiet anxiety. What will happen when there is no longer a human hand on the planetary thermostat? The final phase-out plan is published in the 72nd year after the first flight. By then, atmospheric carbon dioxide has fallen enough that most of the temporary cooling can be removed without causing a dangerous rebound. The remaining greenhouse effect is still stronger than it was before industrialization, but it is declining. Oceans are releasing and absorbing heat according to patterns that models now understand more clearly, though never perfectly. Ice sheets continue responding to centuries of change. Some damage is permanent on human timescales. Some recovery has begun. The plan schedules 8 final release seasons across 12 years. Each one will be smaller than the last. The Council refuses to name a fixed final day. A precise date would create political pressure to proceed, even if measurements advise delay. Instead, the last release will occur when 3 conditions are met. Atmospheric carbon falls below the agreed threshold. Global temperature remains within the safe range for 5 consecutive years, and regional risk indicators show no dangerous divergence. The world watches the conditions as earlier generations watched moon landings, elections, or the approach of storms. The first condition is met, then the second, the third takes longer. A cluster of drought years in 2 regions raises concern that further reduction may be altering circulation. Scientists disagree. Some models show a connection. Others indicate natural ocean variability. The Council pauses for 3 years. People become impatient. Restore the Sun organizes demonstrations demanding completion. Keep the Shield argues that the pause proves phase-out is reckless. Airline manufacturers warn that maintaining dormant fleets is wasteful. Young delegates remind everyone that impatience caused many of the original climate problems. During the pause, rainfall recovers without additional aerosol changes. The event is eventually judged mostly natural, though uncertainty remains. The third condition is declared met. The last release season begins. Only 4 aircraft are needed. One carries Lian, though she is too old to serve as crew. She has been invited as an observer, just as witnesses flew on the first mission. Beside her sits a young atmospheric engineer named Sephu, born after the long descent began. The aircraft climbs before sunrise. Below, the ocean is dark and almost featureless. Above, the sky deepens from blue toward black. Instruments begin their checks. The final quantity is small enough that a large volcanic eruption would exceed it many times over, yet the meaning of the flight is not measured in mass. For more than 70 years, humanity has maintained a layer of deliberate reflection around its world. Now it is preparing to let that layer fade. Sephu asks Lian what she remembers from the first years. She tells him about classrooms where children learn 2 temperature lines. She tells him about the Great Volcano, the unauthorized aircraft, the conflict that broke the monitoring network, and the old analog observatories that kept transmitting. She tells him about Amara, Tomas, Malin, and Idris. She tells him that the system was never controlled by one generation, despite the photographs that always focused on leaders. Were you afraid? Sephu asks. Constantly, Lian says. He looks surprised. The official histories portray her as calm. She smiles. Calm is sometimes what fear looks like when it has work to do. At the release point, the aircraft levels. The valves open. A final measured stream enters the stratosphere. No one says anything for several minutes. Then the valves close. There is no visible boundary between the era before and the era after. The particles already present will remain for a time. Global temperature will not jump. The sky will not brighten suddenly. The climate will not become natural again, because the word natural cannot erase history. The aircraft turns home. Across the world, people watch a simple indicator change from active deployment to monitored decline. Some celebrate, some mourn, some feel nothing at all. In Idris's district, his granddaughter checks soil moisture before planting. In a coastal city, children play on a park built where a flood barrier once stood. At a direct air capture facility, compressors continue running. In the Arctic, researchers measure sea ice. In a tropical forest, observers record the first flowering of a tree whose range has slowly moved uphill. In a hospital, a nurse treats a patient during an ordinary heat wave that is still dangerous, though less extreme than those of the long heat. The end of deployment is not the end of climate work. It is only the end of one chapter. For the next decade, aerosol concentration declines. Sunlight at the surface increases slightly. Ozone chemistry moves toward its non-intervention pattern. Temperatures remain broadly stable because carbon dioxide has fallen enough to compensate. Some years are warmer, some cooler. Natural variability becomes more visible again in public discussion, though it had never disappeared. Every warm year brings nervous headlines asking whether termination shock has begun. It has not. The phase-out was too gradual, and greenhouse forcing too reduced for the rapid rebound once feared. But the anxiety reveals how deeply the program shaped perception. People had learned to see temperature stability as something maintained actively. Trusting a lower carbon atmosphere feels strangely passive. Scientists continue monitoring with the same intensity. The aircraft fleets remain in reserve. Strategic materials are stored. Reintroduction plans exist, though using them would require a new international authorization. The knowledge is preserved, not celebrated. 10 years after the final release, the Council holds a review. Global average temperature remains within the target range. Heat extremes are manageable relative to the earlier trajectory, though they have not vanished. Ocean acidification is slowly easing as atmospheric carbon declines, but deep ocean recovery will take far longer. Sea level is still rising because ice and oceans respond over long timescales, though the rate is lower than in the worst projections. Ecosystems show a mixture of adaptation, recovery, and irreversible loss. The report refuses a single verdict. Climate engineering reduced warming quickly. It likely prevented many deaths and losses. It altered regional climate risks unevenly. It created political dependence and new forms of inequality. It bought time for emissions cuts and carbon removal. It also made postponement more tempting. It required unprecedented cooperation. It generated new opportunities for unilateral action. It did not solve climate change. It changed the conditions under which climate change was solved. This may be the most honest answer to the question we began with. If climate engineering could cool the whole planet, the result would not be a simple rescue and not a single catastrophe. It would be a new relationship between civilization and the systems that make civilization possible. Human beings would know that they could change global temperature deliberately. That knowledge would remain even after the aircraft stopped flying. Every future generation would inherit not only a climate, but a capability. The world would have crossed a psychological boundary. Before, climate seemed vast enough to absorb human activity, until emissions proved otherwise. Then it seemed damaged, but still beyond direct control. Climate engineering would reveal a third condition. The planet could be influenced intentionally, yet never controlled completely. That difference between influence and control would become central. A thermostat suggests certainty. Set the number, receive the temperature. The Earth would never work that way. A chosen global average could still contain floods, droughts, cold snaps, heat waves, storms, failed harvests, and beautiful ordinary seasons. Weather would remain chaotic. Regional effects would remain unequal. Ecosystems would continue surprising models. Human institutions would continue making mistakes. The technology might be precise in how much sunlight it reflected. The world receiving that change would remain complex. And perhaps that would be one of the central lessons of the climate engineering era. Power does not simplify the thing over which power is exercised. Sometimes it reveals complexity more clearly. Long after the final aircraft lands, the institutions built around the program do not disappear. The Climate Council becomes a broader planetary systems assembly. Its authority is narrower than some once feared and wider than anything that existed before the long heat. It cannot set weather. It cannot order nations to redesign every economy. But it maintains shared observation of the atmosphere, oceans, ice, forests, and carbon stores. It verifies large activities capable of affecting planetary systems. It preserves emergency plans that everyone hopes will never be needed. Most importantly, It keeps the habit of asking who carries the risk. That habit influences decisions far beyond climate engineering. When a proposal is made to fertilize part of the ocean to increase carbon uptake, the assembly asks not only how much carbon might be stored, but what could happen to food webs, oxygen levels, coastal fisheries, and communities far from the test site. When companies propose enormous reflective structures in space, the assembly asks who would control them and how they could be removed. When new crops are designed for a changed climate, it asks who owns the seeds. When coastal defenses redirect water toward neighboring shores, it asks whose safety is being purchased with whose danger. The great legacy of the cooling system may be institutional humility. Not humility as weakness, and not the refusal to use technology. Humility as the practice of measuring what cannot be predicted perfectly, listening to people outside the center of power, building reversibility where possible, and refusing to confuse a successful average with universal benefit. This principle is never followed perfectly. No principle is, but it becomes part of what citizens expect from planetary decisions. There is another legacy, more personal. Human beings begin to experience sunlight differently. For most of history, sunlight was immediate and unquestioned. It arrived each morning without appearing on a government budget. People complained about too much or too little, prayed for rain or clear skies, built shade and windows, followed seasons, and rarely imagined that the brightness of the whole planet could become a matter of public policy. During the intervention era, sunlight acquired paperwork. It appeared in annual reports, legal agreements, aircraft schedules, ecological forecasts, and political speeches. A fraction of 1% became something debated by billions. After phase-out, many people feel relief that sunlight is no longer adjusted deliberately. Others miss the sense that someone was watching over global temperature. Both reactions reveal how thoroughly the program entered culture. A museum opens in the city where the first vote occurred. The building is designed around a tall central chamber open to natural light. Suspended above the floor hangs the first aerosol aircraft, its wings stretching almost from wall to wall. Beneath it stand the original council desks, Amara's marked document, Tomas's particle instruments, Maline's crop maps, Idris's jar of dust, and one of Lien's printed continuity manuals. Visitors move through rooms describing the long heat, the first release, regional disputes, the paired obligation, the volcano, the unauthorized flight, carbon removal, the communications failure, and the long descent. No room is labeled victory. No room is labeled disaster. At the end, visitors enter a circular gallery containing testimonies from people across the world. A nurse describes fewer nights when hospital wards overflowed during heat waves. A farmer describes rainfall changes that forced his family to leave their land. A coral ecologist explains how cooling reduced thermal stress while acidification continued. A pilot remembers releasing particles into an atmosphere that looked empty and knowing the act would be discussed everywhere below. A student says she grew up angry that older generations had left her a system that could not be stopped quickly. Another says the system gave her city time to adapt. The testimonies disagree. The museum keeps them together. One afternoon, a school group visits while Lien, now very old, sits unnoticed on a bench near the aircraft. The children have prepared questions. Did the planes make clouds? Could people see the particles? Did the whole world become colder at the same time? Why did some places get less rain? Why did they keep burning fuel if they knew it was dangerous? Why did they not remove the carbon first? Their teacher answers carefully. Sometimes she says, "We do not know." Sometimes she says, "They knew, but changing everything took time." Sometimes she says, "Some people benefited from waiting." A child notices Lien's visitor badge and asks whether she worked here. "A long time ago," Lien says. "Did you control the weather?" "No, the temperature?" "Not exactly." The child looks dissatisfied. "What did you control then?" Lien thinks for a moment. We controlled a small part of what was pushing the temperature, she says. And we tried to control ourselves while we did it. The teacher becomes very still. The child asks the next question before anyone can turn the sentence into a quotation. Was it safe? Lien looks up at the aircraft. It would be easy to answer with the record. The program never produced the global catastrophe its strongest critics feared. It reduced temperature close to intended targets. It avoided sudden termination. Its worst effects were regional, political, and difficult to measure, not an apocalyptic failure. Yet safe is not a single condition. A bridge can be safer than the flood beneath it and still have weak rails. A medicine can save lives and cause harm. A city can be safer on average while one neighborhood remains exposed. A climate intervention can reduce total risk while creating new risks that particular people never agreed to carry. It was safer than the path we were on, Lien says at last. But that did not make every part of it safe. The child accepts this more easily than many adults once did. Perhaps children are accustomed to answers containing two truths. The group moves on. Lien remains beneath the aircraft as sunlight crosses the floor. The beam is ordinary. No instrument in the room is adjusting it. Yet it is not the same sunlight that touched the Earth before industrialization, because the atmosphere, ecosystems, and human world have changed. Ordinary does not mean untouched. She closes her eyes and remembers the final flight. She remembers telling Sephu that calm was fear with work to do. Now there is less work. Not none. There will never be none. Carbon stores must be monitored. Forests must be protected. Cities must continue adapting. Emissions cannot be allowed to return. The reserve fleet must be maintained until future generations decide it is no longer necessary. Climate science will continue because the planet will continue changing. But the great emergency rhythm has softened. The world no longer wakes each year expecting the temperature line to climb without limit. Children no longer grow up assuming every summer will exceed the last. The future contains uncertainty, but not the same accelerating dread. This, perhaps, is what the technology truly purchased. Not a restored past, not a perfect climate, a future that became slower enough to choose within. That benefit would be enormous. It would also be easy to misunderstand. The aircraft would receive attention because they were dramatic. Carbon removal machines would appear in documentaries. Global votes would fill history books. Yet most of the successful outcome would depend on less visible work. Insulating homes, changing industrial processes, restoring wetlands, improving public transport, protecting forests, building clean electricity, designing fairer institutions, sharing measurements, maintaining equipment, and telling the truth when data were inconvenient. Climate engineering could cool the whole planet. But civilization would still have to do almost everything else. It would still need to stop adding greenhouse gases faster than natural systems could absorb them. It would still need to remove carbon already released. It would still need to adapt to changes that could not be undone quickly. It would still need to protect people from heat, flood, fire, hunger, displacement, and disease. It would still need to decide whose knowledge counted and whose losses mattered. A cooler average temperature would make many of those tasks easier. It would not perform them automatically. The museum preserves that difficult truth without turning it into a slogan. That is why it keeps Idris's jar of dust beside the aircraft. One represents power over a small part of the sky. The other represents the lives beneath it. Outside the museum, in that distant future, evening arrives. The school group has gone home. The first aircraft hangs silently above the empty floor. Idris's jar of dust rests inside glass. Amara's document lies open to the sentence that took 11 years to negotiate. No region may be treated as expendable. A museum attendant walks through the gallery, checking doors and dimming displays. The testimonies fall silent one by one. The nurse, the farmer, the coral scientist, the pilot, the angry student, the grateful student. Their voices disappear, but their disagreement remains preserved, because a truthful history does not force everyone into the same conclusion. At last, only the central chamber remains lit. Sunset enters through the high windows and touches the wing of the aircraft. For a few minutes, the white surface glows amber. Then the light moves upward, thins, and fades. Nothing in the building follows it into the sky. No aircraft climbs. No valve opens. No council votes. The atmosphere above the city continues its immense circulation, air rising and falling, winds crossing coasts and deserts, water evaporating from seas, clouds forming and dissolving, heat moving from one latitude to another. Carbon dioxide molecules absorb and release radiation. Oceans carry warmth through currents. Forests breathe. Ice reflects the last light of day. The planet is not unmanaged. People still influence it through every field, road, power station, forest, and city. But the deliberate layer of cooling has faded, and the world is stable enough to continue without it. The attendant switches off the final display. The aircraft becomes a dark shape beneath the ceiling. Outside, the first stars appear. Now let that distant scene drift away. Let the council room, the aircraft, the maps, the arguments, and the long descent move farther from you. They belong to an imagined future, one possible path among many. Here, tonight, you do not need to decide the temperature of the world. You do not need to balance monsoons, ice sheets, forests, oceans, harvests, and sunlight before you are allowed to rest. The questions are real, and serious people are studying them with care. But no single mind must hold the entire climate at once, especially not in the quiet hours when the body is asking to sleep. So allow the planet to become large again. Not a dashboard, not a target, not a problem waiting on your bedside table. A round world turning slowly through darkness, cloud bands curling over oceans, city lights scattered along coasts, deserts cooling after sunset, forests releasing the warmth of the day, mountains standing beneath thin cold air. Somewhere, researchers are watching instruments. Somewhere, engineers are improving clean energy systems. Somewhere, people are restoring soil, wetlands, and trees. Somewhere, negotiators are arguing over difficult language because difficult language sometimes becomes a promise. And everywhere, beneath all of that work, ordinary people are ending ordinary days. Windows are closing. Lights are going out. Fans are slowing. Blankets are being pulled closer. The atmosphere moves above them without sound. Perhaps one day humanity will possess the ability to cool the whole planet deliberately. If that day comes, the greatest achievement may not be the cooling itself. It may be learning to hold such power without mistaking it for mastery, to use it without abandoning the harder work beneath it, and to release it when it is no longer needed. For now, the imagined aircraft is grounded. The museum is dark. The last sunlight has gone from its wings. And there is nothing more you need to carry from this story tonight. Let your jaw soften. Let your breathing find its own quiet rhythm. Let the weight of your body settle more completely into the bed, the pillow, the blanket, whatever is holding you now. The world can remain complicated until morning. The atmosphere can continue its patient circulation. The oceans can keep their slow movement beneath the night. You are allowed to be still. Thank you for spending this time with me, imagining a future in which humanity could cool an entire planet, and discovering that the hardest part would not be making the temperature fall, but deciding how to care for everyone living beneath the changed sky. If you are still awake, that is all right. There is no deadline for sleep. Just let the thoughts become less distinct, like the final shapes in a room after the lights are turned off. Let the aircraft fade. Let the maps fade. Let the numbers fade. And whenever you are ready, let sleep come quietly, without effort, exactly where you are. Sleep well, and I'll see you next time for another quiet journey into another enormous question. Good night.